In our previous videos, we learned about self-attention and multi-head attention. Attention helps the model understand which words are related to each other. But after collecting information, the model still needs to process it and make sense of it. That processing is done by the feed-forward neural network, or FFN. In this video, we'll understand what FFN is, why it is needed, and how non-linearity makes transformers powerful. Inside a transformer block, attention comes first. After attention, we apply the feed-forward network. Attention mixes information between words. FFN processes that information inside each word. You can think of attention as gathering ingredients and FFN as cooking the food. Let's take a simple sentence. AI changes everything. Attention connects AI with changes and changes with everything. But connecting words is not the same as understanding them. We still need a component that can think, transform, and interpret meaning. That component is the feed-forward network. FFN is a small neural network applied to each token. It has two dense layers and one activation function in between. First, it expands the information. Then, it applies nonlinearity. Finally, it compresses the information back. The same FFN is applied to every token. Mathematically, FFN looks like this. FFN of x equals the maximum of 0 and x multiplied by W1 plus B1 multiplied by W2 plus B2. You don't need to remember the formula, just remember this idea. First, expand the information, then apply nonlinearity, and finally, compress it back. Now let's understand what nonlinearity actually means. Imagine a simple linear function. If the input doubles, the output also doubles. This is straight line thinking. Here's something important. Even if you stack many linear layers together, the result is still just one big linear function. No matter how deep the network is, it still thinks in straight lines. And that is a problem. Language is not linear. Consider this sentence. I am not happy. The word happy is positive, but the word not completely flips the meaning. A small change in input creates a big change in meaning. That behavior is nonlinear. Let's look at some real-life examples. Think about a light switch. It is either off or on. There is no gradual transition. Or think about exam results. 49 marks means fail. 50 marks means pass. Just 1 mark difference, but the outcome changes completely. This is nonlinearity. Inside FFN, nonlinearity comes from the activation function. Common activation functions are ReLU and GELU. Modern language models like GPT use GELU. Without this activation function, FFN becomes useless. Nonlinearity is what allows the model to learn complex patterns. Another important point is that FFN is position-wise. Each token passes through the same FFN independently. Tokens do not interact with each other here. All token interaction already happen inside attention. FFN focuses on transforming each token's meaning. Let's take another simple sentence. ChatGPT writes code. Attention connects the words. FFN understands that ChatGPT is an AI tool. Writes is an action and code is technical content. FFN converts raw information into meaningful representation. After FFN, the output is added back to the original input. This is called a residual connection. It prevents information loss, stabilizes training, and allows very deep transformers to work properly. In GPT-style generative models, attention and FFN blocks are stacked many times. FFN layers learn grammar, reasoning patterns, and writing style. In fact, most parameters in large language models live inside FFN layers. Let's summarize. Attention mixes information. FFN processes information. Nonlinearity enables learning. FFN is applied to each token. Without FFN and nonlinearity, transformers would understand relationships but not meaning. In the next video, we'll learn about residual connections and layer normalization. These techniques keep large language models stable and trainable. If this video helped you, like, share, and subscribe to My Tech Notes.